Okay, all right, let's get started. So I want to finish the lecture on FFT. There is still some amount of work to do to finish that, right? So recall, what are we trying to do? We are trying to find a fast algorithm to multiply two polynomials, right? The naive way to multiply two polynomials, the way we define things would take n square time if you have two degree n polynomials, and we want to do it much faster, right? We're aiming for something which is n log n, right? So what was the basic idea? The basic idea was basically divide and conquer. After we think about changing the representation of a polynomial from a coefficient form to a sample representation, right? There are two ideas basically, right? One idea is that, let's think about polynomials not in the standard coefficient representation, but in the sample representation. So what is a sample representation? That I evaluate the polynomial at some n points and keep the values of those n points, right? That's a way of representing the polynomial, right? Now, what is the second idea? The second idea is that if you choose the points where you evaluate, you have the freedom to choose wherever you want to evaluate them as long as they're distinct numbers. If you're careful about the choice of the points where you want to evaluate the polynomial, then you can evaluate all the polynomial and all the n points more efficiently than just evaluating them one by one, taking n time each, right? That would take n square time again, so which is not very useful. But if you choose the points carefully, then you will get speed up, right? So let's do an example, or just sort of this as the divide and conquer strategy we designed. So this is a degree 8 polynomial, degree 7 polynomial. So we think of it as having 8 coefficients, right? Starting with the constant term, which has degree 0 all the way to degree 7. So what was the basic idea to do divide and conquer? We broke it up into the sum of even degree coefficients and odd degree coefficients, and then we can factor out x, and so basically we can write the polynomial as a sum of two polynomials, right, of half the number of coefficients, right? But its important thing is that this is if you think of this as a polynomial with 4 coefficients, right, we want to think of the variable here as x squared, not x, right? So this is a polynomial. In changing the variable from x squared to x, then we get a smaller polynomial of half the degree, right? So that is the key, right? So if I want to evaluate this polynomial on some set of numbers, some samples x0, x1 up to x7, what do? I take the square of this set. What is the square of the set? I take the square of all these numbers. Okay, that's the square of x. Now we wanted to have some, if you had some magical set which had the property that when you take the square of the numbers, we get half the set, right? Somehow by magic, if you had such a family of numbers, then something nice will happen, right? So let's assume that the square of the x is basically these 4 numbers, right, without loss of generality. There may be, we can renumber and we can think of them as those numbers, right? Okay, so now if I want to evaluate this polynomial on each of these 8 numbers, what do? I first compute the square of all the numbers, right? That's just linear time. And then I look at this polynomial. This polynomial, I'm thinking about it as a degree 3 polynomial, not as a degree 6 polynomial, but a degree 3 polynomial, right? That makes sense? Okay, so we'll call this a even, and then we evaluate a even on the square of x. So I'm writing this degree 3 polynomial as its coefficient representation 5, 3, minus 10, and 11, right? And then we also look at the odd degree, which is the odd degree polynomial with x factored out. We get another degree 3 polynomial, 2, 7, 1, 3, and we evaluate this also on the square of x, okay? So what did we do? We took the problem of evaluating a degree 7 polynomial on 8 points, right, that has 8 coefficients on 8 points. If we had this magical property for x, we can break it down into 2 problems of half the size, right? Now once I have the value of this polynomial on the square of x and this polynomial on the square of x, I can compute this polynomial on x, right? That's easy to see, yeah? So in linear time. So then if you do this, well, how do we solve this? We solve it recursively, right? What do? I mean, we take this is a degree 3 polynomial with 4 coefficients. We again break it up into 2 polynomials, right? With coefficients 5 minus 10 and 3 11. But now again, we have to have the property that the square of x again becomes half the size, right? If you had that, we can continue the recursion, and then we'll get the recursion of the term t of n is 2t of n over 2 plus O of n. That will become n log n, right? So so the only thing that we need to figure out is that how do we create this magical set of numbers, right? Which has a property that each time is square, it becomes half the size. And we saw that we kind of realized that we need to get into complex numbers, because even if you want to get a set of size 4, it doesn't work if you don't go to complex numbers, right? Because how do you repeatedly square and the next time basically you'll get the square of -1, right? It seems like not possible with real numbers, and you can formally prove that you cannot have a set of real numbers where this property holds recursively. So we have to go to complex numbers, okay? And then when you go to complex numbers, things work out. And it's not maybe surprising that you need to go to complex numbers, because polynomials are not factorable in real numbers, right? You can only factorize them in the complex set. So it makes some sense that you need to go to complex numbers, right? So okay, so the question is, are there collapsible sets? And it's not hard to convince yourself that you need to use complex numbers, okay? And then even in complex numbers, are there collapsible sets? And we'll see that there are. And just in case you've completely forgotten about complex numbers, let's just quickly review some properties, right? And even I don't work with complex numbers on a daily basis, but they're not, right? Okay, so we for the rest of the lecture, I will stand for the square root of -1, and complex numbers, you can think of them in two ways. They are numbers of the form a plus ib, where a and b are real numbers, right? And you can also represent them as in the polar form, where you write it as r e to the I theta, or which is the same as r cos theta plus I sin theta, right, by Euler's formula. And there are many interesting properties. So what's in some sense, right? Okay, complex numbers are what are called algebraically closed field, right? You start with real numbers, and you see that polynomials don't always have roots, right? X squared plus 1 doesn't have a root. So you kind of extend the field of real numbers by adding, by defining I to be the root of x squared plus 1, and then as soon as you add one root by basically just making it up, right? It turns out that all polynomials factor, right? It suddenly becomes algebraically closed, right? It's not true for all fields that you add the root of one polynomial and somehow it becomes magically, but it just happens to be the case for real numbers, right? So so there is this terminology called algebraically closed, and so what other properties do we want? Well, Euler's formula, I assume, right? E to the I theta is cos theta plus I sin theta. It's how do you define exponentiation in complex numbers? By this series way, okay? So let's see. Okay, now let's look at how do we create collapsible sets, right? It turns out that basically the roots of unity will give you the collapsible set. Okay, so what is the roots of unity, right? So here is a polynomial, right? X to the k minus 1. Okay, what are the roots of x to the k minus 1, right? Okay, clearly 1 is a root, right? But when you can write x to the k minus 1 as x minus 1 times 1 plus x square up to x to the k minus 1, right? You can factorize x to the k minus 1 as x minus 1 times 1 plus x square up to x to the k minus 1, right? Now, so 1 is clearly a root, right? Now, what are the other roots? All the other roots are complex, right? Okay, what are the k roots? Basically, these are multiples of e to the 2 pi. I mean, they're all of the form. So okay, let's define the omega k as e to the 2 pi I by k. Right here, I is the imaginary number, right? And all the other roots are basically multiples of this, right? So they are powers of this, not multiples of this. So it is the 0th power is 1. No, I guess here 1 is missing here, right? The first power is missing. That should be this. This should be 1 here, right? So the powers of omega k are from 0 to k minus 1 are the roots of this polynomial. How do you see it? If you raise this to the k, right? If you take let's say you take any power of I mean, okay, it's a little bit confusing because I is the imaginary number and we're using the index j, right? If you raise it to the power of k, what happens? You get e to the 2 pi ji, right, for some integer j, okay, and that is 1, right? Okay. In the complex plane, how does it look, right? If you think about the complex plane, you take the circle, right, in the polar form, okay. So basically, this angle is 2 pi over k, okay. So that's the first guy. Then you take another 2 pi over k. That is the second. This is the 0th power. Is the first power. Is the second power, and you go all the way around the circle, right? And you get the k roots of unity. Okay. All right. First, I mean, it's easy to verify that they do satisfy the polynomial and they are distinct. So we have k roots, and because of the fundamental theorem of algebra, they have to be the roots, right? Because of the uniqueness, right? Okay. Now, so that's good. What is the thing we want? We want to claim. Well, this is just claiming that they are the roots of unity. Some observations, right? Because of this circular form, one is that these are simple observations because of the circular nature. If you, for any j, if you look at the jth power of that kth unit of unity, it's the same as taking j mod k, right? If j is bigger than k, you'll come back to j mod k, right? So I mean, just that in the circular form that holds. And what are the other properties? That basically omega k is the same as omega jk raised to j. Okay, that is basically every kth root is also a jkth root. Okay, and this is simple. Just from the formula you can figure this out. Okay, and what is the other property? I also claim that remember that x to the k minus 1 is x minus 1 times 1 plus x plus up to xk minus 1, right? Okay, because each of these guys is a root. If I plug it into that that factorization, you have to have the property that 1 plus omega k to the so this is take any j where j is not equal to 0. We know that omega k raised to the j is a root of unity, right? So if you plug it into the polynomial, it will become 0. But it's not 1, right? Because remember, x to the k minus 1 is x minus 1 times this, right? And if j is not equal to 0, x minus 1 is not 0, right? So the rest of it has to be 0. So that simply means that 1 plus omega k raised to the j, omega k raised to the 2j, omega k raised to the k minus 1 times j should be equal to 0 for any j not equal to 0, right? But every other root has to satisfy the second part is, so all this is saying is that it is saying that if you factorize x minus 1 as this one, if this is a root of this and is not equal to 1, then this must be equal to 0, right? If you plug it in, it should be equal to 0. Okay, so we'll use this property later on. It's not important right now. Okay, so the main claim is that if n is a power of 2 and you take the nth roots of unity, then they form a nice collapsible set. Okay, so that's the claim, right? And once you have that, that's it. We got our magical set, right? Okay, so now let's just verify why is it that the nth power of unity for n is when n is a power of 2 form a collapsible set. Well, you take all the nth power of these roots and you square them, they become the roots of the n over 2 powers of, they all become the n over 2 powers of unity, right? And that's it. That's a simple observation. Okay. If you had this, then by recursion it will happen, right? So you take the nth powers of unity, you take the squares, they suddenly become the n over 2 powers of unity. Well, by induction they'll become, if you take the squares again, they'll become n over 4th power of unity and so on, right? Okay. So now so let's look at some examples, right? What is x1 is 1, right? x2 is 1 minus 1. No wonder, right? They are the roots of the polynomial x square minus 1, right? Now, as soon as you go to 4, x to the, so we are interested in x to the 4 minus 1. What is x to the 4 minus 1? We know its roots, right? We write it as x square minus 1 times x square plus 1. Okay, what are the roots of x square minus 1? 1 and minus 1. What are the roots of x square plus 1? I and minus I, right? So, we get that nice thing. What about x to the 8? Okay, here it becomes a little bit more messy, right? And once you go to x to the 8, well, it is x to the 4 minus 1 times x to the 4 plus 1. Well, we already know the roots of x to the 4 minus 1, these are the things, but what about x to the 4 plus 1? Okay, what are the roots? Well, all combinations, you take 1 over square root 2 and plus 1 minus 1, here you have to, there are 4 roots, right? These are the 4 roots, okay? But they are all the root, they are basically the roots of the polynomial x to the 8 minus 1. Okay, now let's convince ourselves that this property holds, that if you look at the nth powers of unity and you square them, you will get n over 2 powers of unity, just to make sure that we see the algebra. Okay, it's easy, you can verify it if you want, let's just check that, right? So why does it magically happen? Okay, so what are the nth powers of unity? 1 omega n square up to omega n to raise to the power of n minus 1, right? Where what is omega n? E to the 2 pi over n, right? Okay, now, so that's, I'm just writing that again. It is, you can write this as e to the 2 pi over n times 0, 2 pi over n times 1, 2 pi over n times n minus 1. These are all the roots of, right? Okay, now let's take the square. What happens when you take the square? Remember, n is the power of 2 here, or even number, right? If you take the square, well, this becomes 2 pi over n times 2 times 0, right? 2 times 1, right? You just doubles, right? So I'm just keeping the 2 pi over n separate, right? And just multiplying everything by 2 here, because, right? Okay, now there are how many here? N roots here, and so we take the square. I'm taking the first n over 2 guys, and then I'll worry about the next n over 2 guys later. Okay, let's look at the first n over 2 guys. What happens? This becomes, it still remains 0, so I can rewrite this as e to the 2 pi over n over 2 times 0. I took this 2 and moved it to the denominator. Now this becomes, I'm just moving this 2 down to the n, make it n over 2, right? And all the way, right? What happens? I get e raised to 2 pi divided by n over 2 times 0, e raised to 2 pi divided by n over 2 times 1, all the way. So these are the n over 2 powers of unity, right? I just changed n to n over 2 and went from 0, 1 all the way to n over 2 minus 1, right? These are the, so we got already a set of n over 2 distinct numbers, right? Okay? So those are n over 2 powers of unity. Now what we have to verify is that the rest of these guys will collapse to this guy. Okay? Okay, that's all we need to do, right? If you do that, then we are done, right? Because that means that we have, right? Okay, that's just basic algebra, right? There's nothing. Okay, what are the rest of the guys? The rest of the guys are e to the 2 pi over n, 2 times n over 2 plus 0. I'm just writing it as n over 2. Remember, they are starting at n over 2, going all the way to n minus 1. Instead of writing it as like, in that sense, I'm writing it as 2 times n over 2 plus 0, n over 2 plus 1, n over 2 plus n over 2 minus 1, right? I'm just shifting it by n over 2, okay? Okay, what happens, what are these numbers? These numbers are, well, you know, you get, what happens to this 2 times n over 2? It becomes n, right? And that n and this n will cancel, okay? So I get e to the 2 pi basically, plus, so take this term for example, I get e to the 2 pi plus e to the 2 pi over n times 2 times 1, right? So I took out e to the 2 pi because that becomes 1, right? Okay, so if you look at the remaining, then I can still move this 2 to the 2 below to n over 2, so I claim we get e to the 2 pi outside for everybody, that's 1 which disappears, and then we get, you know, e to the 2 pi divided by n over 2 times 0, e to the 2 pi divided by n over 2 times 1, e to the 2 pi divided by n over 2 times 2, all the way to e to the 2 pi divided by n over 2 times n over 2 minus 1. But these are exactly the same n over 2 powers of unity that we had in the first set. So as a set, they'll just disappear. Okay. This is just verification, right? That we are saying it's a simple observation that if you take the nth powers of unity and square them, you will get n over 2 powers of unity. There are many ways of seeing it, right? You can just look at geometrically, it's very easy. Or maybe geometrically it's easier to see it as if you take the n over 2 powers of unity and so divide them, you'll get nth powers of unity. Okay, maybe that's easier, right? But if you just want to do it algebraically, this is what we're doing, right? You can convince yourself. Okay, there's nothing, right? Yeah. To some extent, yeah. I mean, since in different fields you'll get, you can have more interesting sets, right? But in the field of complex numbers, if you can take different fields, right? But then you can have some interesting sets. But in the complex numbers, this is the one interesting thing. Okay. All right. Okay. So we found our magical set and we are done, right? If you evaluate it on this set, we get what we want. Okay. Okay. So let's recap. We'll actually call it, this has a name. Evaluating a polynomial in the nth powers of unity is basically called the discrete Fourier transform. Okay. All right. And we've seen that we can take any polynomial of degree n, if n is a power of 2, n minus 1 when n is a power of 2, and evaluate it on the nth roots of unity in n log n time, right? And that particular algorithm is called fast Fourier transform. Okay? So there's a distinction between discrete Fourier transform is just a definition which says that I want to take a vector of length n which corresponds to a polynomial of degree n minus 1, and I want to find out all the values of that polynomial on the nth powers of unity. Okay, that's just the definition of what a discrete Fourier transform is. Fast Fourier transform is this particular divide and conquer algorithm to compute that. Okay, okay, there is different, right? One is the algorithm, the other is just the definition of discrete Fourier transform. Okay, okay, so we've seen that you can do this fast Fourier transform in n log n time. Okay, good. Now back to convolutions and multiplications, right? Okay, what were we trying to do? We are trying to multiply two polynomials fast, right? So we said, oh, okay, if you can take two polynomials and go from the coefficient representation to the sample representation, then multiplication in the sample representation is trivial, right? You just multiply all the values, okay, but then you have to come back, right? So what do you get when you multiply the sample representation? You get the sample representation of the product of the polynomials, but you're not interested in that. You want to go back to the coefficient representation, okay? So there's still that a little bit of problem to take care of. So remember, what do we want to do? We want to compute the convolution, which is simply the, if you think of it as polynomials, we want to multiply these two polynomials, right? So So we can compute the values of A and B at some n sample points like we did, right? That is it. And then you compute the sample representation of the product, right? That's easy, right? Because you just multiply all of them. And now you have to go back to the coefficient representation of this. But there's a little bit of catch, right? And this is just to make sure that you understand this, that the degree of the polynomial that we are multiplying is bigger than the original polynomials, right? So you can't just evaluate A and B only at n sample points and recover C. So you have to evaluate A at more points, because you don't have enough information to reconstruct C if you evaluate C only at n points. Okay? Alright, so just to make sure that, so what do? We think of A and B as actually degree 2n minus 2 polynomials by padding with zeros. Okay? Okay, that's a small thing you have to keep in mind, right? Remember, when A and B are degree n polynomials, degree n minus 1 polynomials. When you multiply, we get a bigger polynomial, right? Okay, when we think of coefficient thing, we don't care about that, right? We think of, but when we do when you take the sample representation, if you just take the sample representation of A on n points and B on n points, what happens? You only have n evaluations. For C, you only get n evaluations. But C is of a bigger degree, right? It's not enough to reconstruct C because C has degree 2n minus 2. You need n more, right? You need more points. So we have to make A, we have to evaluate A on more points, B on more points, and then we'll have evaluation of C on the right number of points. Okay? That's something to keep in mind. Okay? So what do? We actually, we actually pad A with some zeros and make it a degree 2n minus 1 polynomial, and same with B, and then we'll have C prime, which is the evaluation of C at the right number of points. Okay? Agreed? Okay. Now, so that's fine, right? Each of these, so we are going to evaluate A and B at the 2n minus 1 roots of unity. We can take n log n time, right? It's still, we increase the size of A by a factor of 2, that's okay, right? N log n is sort of O of n log n. What remains? What remains is that we need to go back from the sample representation of C back to the coefficient representation of C, right? Does it make sense what we're doing, right? We took A and B, we made them into sample representation, and then we got a sample representation of C. But we don't have C in the coefficient form. Does it make sense? We have to go back to what we really want is the coefficient representation of C. But we have a sample representation of C. Okay? Does it make sense? Questions? Okay. Alright. So how do we do that? Right? That's called the inverse Fourier transform. Okay? Okay. Remember, what is the Fourier transform? If I give you the coefficient representation of a polynomial, the discrete Fourier transform is give me the values of this polynomial on nth powers of unity, right? The inverse Fourier transform is I will only give you the valuation of the polynomial on nth powers of unity, you construct the coefficient representation. Okay, if you can do that also efficiently, then we can do the convolution, right? We go from the coefficient representation of A to the sample representation, coefficient representation of B to the sample representation, multiply them, we get the sample representation of C, and now we can go back to the coefficient representation of A. Okay? So that's called the inverse Fourier transform. We need to be able to do this also efficiently if you want to finally get a proper efficient algorithm for the complete multiplication, right? Otherwise we are not done. Okay? Okay. So how do we do that? Well, so that's the problem. Given the evaluation of an n minus 1 degree polynomial A on the nth roots of unity, and we'll specify that evaluation values as A prime, another vector, right? It's also 1 for each point, so that's another vector of size n, right? So how do we go back to A? I don't know A, I only know A prime, so I want to go back to A. Okay? So we saw that A prime can be computed from A in n log n time, can we go compute from this? Okay. So how do we think about it? It's most convenient to think of it in a matrix format. Okay? So what do we know? What is the relationship between A and A prime, right? The relationship between A and A prime is that what is what is A naught prime? A naught prime is the evaluation of A on x naught, and A1 prime is evaluation of A on x1, where x naught, x1 up to xn minus 1 are the nth powers of unity. So what does it mean? That means that Aj prime is Aj is A naught times 1 plus A1 times xj plus A2 times xj square and so on, right? So we can write the sample representation as this matrix times the vector representing the coefficients. Does that make sense? Yeah? Okay. Now, what we did was we said that if you pick this x0 up to xn minus 1 as the nth powers of unity, you can compute this from this in n log n time. But what do we want? We want, now we have this, but we want to compute this. Right? Inverse Fourier transform is I give you this and I want to compute this now. Okay? Okay. So remember x0, x1 up to xn minus 1 are not arbitrary, right? They are precisely the nth powers of unity, right? So we will replace the x0s by the omegas just to, right here, I mean, just to avoid the notational confusion, I will just call the e to the 2 pi over n as omega instead of omega subscript n, just to avoid notational overhead, right? So what do we have? We saw that, you know, given a naught up to a n minus 1, you can compute a naught prime up to a prime n minus 1, the discrete Fourier transform, using f of t in n log n time. Now we want to invert that process. Okay, but in this matrix form, it is simply a naught up to a n minus 1 is the inverse of this matrix times the sample representation, right? Okay, this looks complicated, right? Oh man, how am I going to do this matrix inversion, right? But this matrix is not arbitrary. It's a very nice matrix because these are nth powers of unity, right? And this has a nice structure that is called a Van der Waals matrix. And so you say, okay, what do we do? Again, you know, somehow magic happens because of math, right? And these are not arbitrary. And so it turns out that the inverse, you don't have to do any computation. It is exactly 1 over n times, you replace every omega by omega to the minus 1. Okay? I mean, you can verify it, we'll verify this, okay? So the inverse of that matrix is just, you know, a scaling factor of 1 over n times you replace all the omegas by omega to the minus 1. Okay? So that's, I mean, we can verify that. Suppose you believe me. Okay? If you believe me, then what are these, right? What is this? This is another Fourier transform, except that what is omega to the minus 1, right? It is just a shift, basically. Okay, so see, remember, what is this? This is 1, 1, 1, 1 omega, omega. So this is the one root of unity, this is the next root of unity, this is the n roots of unity, right? What are these? Here you have one root of unity, this is another root of unity. All of these are again roots of unity except that they are permuted. Okay? What is omega to the minus j? It is e to the minus j 2 pi over n, right? Okay, but that is just simply the same as n minus j to the 2 pi over n, right? Because I can add 2 pi n to this, right? Right? This is the same as this, right? Okay, so this omega to the minus 1 is nothing but omega to the n minus 1, right? Instead of seeing them in 1, 2 up to n minus 1, we are seeing them in n minus 1, n minus 2 up to n, right? Okay, so computing this thing is the same as computing a fast Fourier transform, right? Because except for the scaling factor 1 over n. Okay, remember, what do we want to compute? We want to compute this times this, right? Well, what is this? This is the matrix inverse. What did I claim it was a matrix inverse of? It turns out to be, by magic, a permutation of the original fast Fourier transform matrix. So my claim is, okay, maybe this is, okay, so remember, we know how to compute this fast, right? If I give you this, computing this product is n log n time. What does it mean computing this product? That is to evaluate this polynomial and all these points can be done efficiently, right? Well, when we look at it the other way, what we want to say is that, I want to compute this and I want to do it with the inverse of this time, right? What do we have? We have this vector, right? And I want to compute this, but the inverse of this turns out to be just a permutation of the standard matrix that we saw, except that we have this extra scaling factor, this, okay? So what do? You take this A prime vector, think of that as a polynomial now, evaluate that polynomial on the nth powers of unity in n log n time, and then scale them down by 1 over n and permute them, and you will get the value a0 up to a1, an minus 1. Yes?
So do we treat these that we found earlier as the coefficient of the new polynomial?
Yes, yeah, I mean, so when we multiply a and b, we get c, right?
Yeah.
We want the c, we only have the sample representation of c.
Yeah.
So that means that means that we think of that as now a vector now. Okay, think of that as a polynomial.
So we treat c as the coefficient of the polynomial.
We don't have the coefficients of c. We only have the sample representation of c.
Yeah.
Okay, so call them c0 prime, c01, cn minus 1. Okay, so we only have the primes. That is, we have the evaluation of c on the nth powers of unity. We don't have c.
C is what
We are looking for c.
and we treat c prime as
No, yeah, we treat c prime as a polynomial, even though it is not, and then compute its discrete Fourier transform, like we did without not worrying about the fact that it is a sample representation. And to get c, what do? You would scale everything by 1 over n and permute the rows, right? Why does it work? Because of this magic. The inverse of the Fourier transform FFT matrix is 1 over n times a permutation of the matrix. Okay? So what is the algorithm? You take A, you pair it with n zeros. Okay? You take B, you pair it with n zeros. Then what do you compute? You compute the fast Fourier transform. What do you say? You compute the discrete Fourier transform. What are we doing when you do the discrete Fourier transform? We are computing the value of A at the nth powers of unity, right? That we know how to do n log n time, right? We do it for B also. We get the valuation of B on this, not n points actually, now 2n minus 1 points, okay? So we get the value of A and A prime to B primes in n log n time. Now we get C primes by multiplying them, right? Each term by term. Now we want to go from C prime to C, okay? Okay, somehow you say, okay, I will treat C prime as a polynomial, even though it's actually the evaluation, and use C prime as a polynomial, and again you do the discrete Fourier transform on that, okay? Even though it's not a, so we'll get in n log n time something, right? Let's call it C double prime, right? It doesn't feel like it has a meaning, but we scale everything by 1 over n. You take C double prime, divide everything by 1 over n, and then invert, you just permute the coefficients of C double prime. That is C by magic. Because of this property that if you take this matrix and look at the inverse, it looks exactly like the standard Fourier transform matrix, modulo the permutation of the, okay? Questions? I see some, okay, yeah.
What do you mean by the inverse matrix is a permutation?
Oh, because, suppose instead of minus 1 you had just omega, okay, then what happens? It looks like that's what the Fourier transform does, right? Right? So what is the Fourier transform in the matrix language? The Fourier transform in the matrix language is precisely, okay, this is the Fourier transform of this, right? What is that? It is simply the multiplication of this by this matrix. Okay, except that when we want to do the inverse, we don't have this, but we have -1 here. Okay, but if I give, instead of giving you, I claim that, if I, instead of giving this, I give you a product with -1s, then I can just permute to get what I want, right?
How would you permute it?
No, because it is just, instead of, so okay, so let's see. What I'm trying to say is that, suppose, so you wanted to do this product, right? Okay, but no, I say, no, I can't give you that. Okay, I'll give you the following product. What is the following product? I say, okay, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Instead, I'll say my omega -1, omega -2, blah, 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 omega minus 2 here, omega minus n minus 1 and stuff, right? I'll give you this and say, let's call them a double prime 0, a double prime 1 up to a double prime n minus 1. Okay? So I wanted to compute the product of this and get this, but I can't give you that, but I'll give you the product of this and give you this. What is the relationship between these guys and that guys? I claim that a prime 0 is just a double prime 0 is a prime 0. What about a double prime 1? What is it? A prime n minus 1. Why? Because this guy is this. Okay, so this guy is this guy is the next guy. So I mean, this matrix is just, all these rows became permuted. Okay, that's it. Just one permutation, right? So instead of giving you this matrix, if I give you this, it's nothing but instead of getting this in this order, I'm getting them in this reverse order. That's all, right?
So is the permutation likewise the same?
Yeah, it's always the same. I mean, in the sense that, it's exactly, we read it backwards. Okay? It's not even like anything complicated. You just read it backwards. Okay? All right? So the inverse Fourier transform is as easy as the Fourier transform because of this magic. Right? All right? Okay? Okay. So, okay, now you have to convince yourself that what I said was true. That is, the inverse of this is this matrix, right? If it is, then you are happy, right? If it is not, then, I mean, I claim that, but I didn't prove it to you. Okay, how do you convince yourself that this is this, right? You can actually multiply them, right? And see that you get identity matrix. Yeah? Okay? Okay, I won't do it for you, okay? Because, you have to do something for yourself, right? Okay, so here is where we use the property that the sum of the powers of unity, if you take 1 plus x square to x to the n minus 1 and plug in any power of unity other than 1, you'll get 0. Okay? Right? So these rows are orthogonal, in fact. Okay? You can check that you can check that the rows of this matrix are orthogonal using that property. Okay? And then you multiply all of them, you'll get the identity matrix, basically. Okay? It's just algebra, right? In the sense that the interesting thing is not the algebra, right? The interesting thing is that somehow these things have nice properties, and that can be exploited algorithmically. All right? Okay, I won't do the algebra for you. It's not hard. You have to convince yourself that's the inverse of the matrix, so we can do the inverse Fourier transform in n log n time, right? By just using Fourier transform and doing some rescaling, right? 1 over n and then permanent thing. Okay, so now you are convinced that you can do convolutions in n log n time, right? Yeah, the big picture is clear. You go from the polynomial coefficient representation to sample representation, where the samples are basically the nth powers of unity. Once you have the sample representation, multiplication is easy. Then you do the inverse Fourier transform to get the original coefficient, the coefficient representation of the product. Okay? So it takes basically 3 fast Fourier transforms to do convolution, right? Yeah? 2 for A and B, multiply, and 1 inverse, right? Inverse is the same as, right? Yeah? Questions? Yeah? Okay. So at the end of this, what do we have, right? We have a very powerful primitive, right? What is a powerful primitive? That somehow this very non-obvious thing of how do you take 2 polynomials of degree n and multiply them, we get magically, we can do it in n log n time, which is far from obvious, right? It seems, there's a big difference between quadratic and n log n. Okay? You take, n to be, 10,000, right? There's a big difference between quadratic and, right? So you, and this FFT, if you look at this divide and conquer thing, it has a very nice, you can implement it in hardware, in fact. That's what many chips do. They implement specific sizes of FFT in hardware, and it is, there are some nice combinatorics of the FFT circuit. I won't go into it, but it looks quite pretty. It's, you can follow up on that. There are some issues to deal with because of the numbers involved, right? We are multiplying polynomials and numbers kind of blow up. Okay? We ignored all the numerical issues. How do you deal with complex numbers? The numbers getting very big, all this, right? Yeah, they are not, they are a bit painful. Okay? So so we'll ignore that issue because it's beyond the scope of this at this point. But the thing is, the use of fast Fourier transform in science and engineering is not basically for the reasons of discrete algorithms. It's mainly for signal processing. Okay, so you take a signal and you do the discrete Fourier transform, then you can get the frequencies, and that's the reason why discrete Fourier transform is used. Okay, and that it has many applications and stuff, right? But what I want to, so we'll not go into that. For some of you who are familiar with Fourier series and stuff, you can imagine the applications. What I want to tell you is that FFT is also this magical thing because it does this convolution in a very non-obvious way. I want to give you one application which is, a very strange and nice application in a black box fashion to what's called pattern matching with don't cares. Okay, so the idea is that I somehow know that I can do FFT fast, and you don't even need to know the details, right? If the convolution can be done in fast, can you use it in algorithms, right? Which seem very far away from. So we'll do some string matching application, right, to illustrate the power of FFT, right? So here is some basic string matching that many of you see in various forms, right? What is the basic string matching problem, right? I give you a big text and I give you some smaller text, and I want to know, is this in the big text or not? A pattern, right? Okay, that's the basic string matching problem, right? Have you guys thought about that before? How to do it? Right? Some of you might have thought about it, some of you not, right? How would you do it? So I give you, we do it all the time, no? In the web browser and your computers and your editors, right? You're searching for a string, right? Your name or something, right? How do you do it fast? Okay, so for concreteness, let's say the string you're searching for is of length m. Okay, and there's a big text of length n, right? Typically, we're searching for a small thing and a big thing. What is the most natural, silliest thing we can do, right? Sorry? Oh, that's not the most natural algorithm. I mean, okay, KMP algorithm is well-known algorithm, right? But the silliest thing you can do is put the text in each position and check, does it match, right? You have an n-length string, you put the text in, align it with the thing, and check all the characters match, right? If you do that, that will take nm time, right? Right? Every position of the text, you put the pattern, right? Okay. But as you said, there's this very fancy KMP algorithm, right? How do you get KMP algorithm? Let's do it in a slightly different way, right? KMP algorithm is very clever, okay? But let's do something which is a little less clever, but still interesting. You can convert the text into an NFA, no? Okay, no, the pattern into an NFA. Okay, okay. So that's if you, how many of you have seen automata theory? How many have not seen? Let's say. Okay, okay. So this is just, don't worry if you don't know, right? But this is just to remind you of the interesting application of automata theory. Is that suppose I want to search for algorithms, right? In some big text, right? Okay, so what do? I create an NFA for algorithms, right? So what I do is, I think of it like this. Sigma, and then, here is an NFA, right? What should I do? I have L, right? I can create an NFA from just the pattern, right, of length, how big, of length m, okay? And now I claim that, what does this NFA accept? What is the set of all strings that this NFA accepts? Sorry? No. Remember, it accepts, no, that's not what it accepts, right? It accepts algorithms for sure, but anything which has algorithms it will accept. Right? Exactly. Any string which has algorithms it will accept. Okay? So given the pattern, we can create a small NFA such that the only strings that this NFA accepts are precisely all strings which have algorithms in them, right? Or whatever thing, right? Okay. So, well, this is not an NFA, but we can convert it into a DFA, right? Okay. Okay, what is the advantage of converting into a DFA? Suppose we convert it into a DFA. How big will the DFA be? Sorry? It can be at most 2 to the m, right? Because the NFA size is m. It can be at most 2 to the m. Now, once you have a DFA, what is the advantage? You can, if I have a big string, how long does it take for me to check whether given a fixed DFA, how long does it take to check whether a string is accepted by the DFA? I just simulate the DFA, right? What is the nice thing about DFA? It just looks at one character at a time. Okay? So, I can just run the string through the DFA, and it only takes linear time in the length of the text that I need to do. I can stream the text through the DFA, because that's nice thing about DFA, it doesn't look back and stuff, it just keeps changing states, right? Okay? So, once you have the DFA, it's linear time. Okay? Okay, but the size of the DFA I need to construct could be up to 2 to the m. Right? So, you can do it in 2 to the m times n, which doesn't look that nice, right? Okay, I mean, but no, it's not 2 to the m times n, it is basically 2 to the m for fixed. I initially create 2 to the m. Once I create the 2 to the m, I can use the same DFA for any number of text. That's the advantage, right? The pre-processing time is 2 to the m, but then it's just n time. Okay? So the KMP algorithm, Knuth-Moritz-Platt algorithm, reduces that 2 to the m without actually creating the DFA explicitly to m plus n. Okay? So you can do this, a very clever algorithm which is built on this idea of DFAs, right? Which can do that very quickly. But now, I mean, we're not going there. What we're going to do is something which is a bit more complicated problem, and that is, I want to compute, I have, my pattern matching problem is a little bit more complicated. Okay? What do I have? I have don't care symbols. Okay? Star. Okay? Star matches with anything. Okay? So here is an example. So suppose my pattern is A star star, and my text is, this aardvark, right? What does this match, right? What are all the matches of this? So this will match AAR, and it also matches ARK. Right? Sorry? And also ARD actually, right? Yeah? So those are all the matches, right? So there is so I have a more complicated problem here. Okay? Now can you also do this with NFA? You can, okay? Except that there is no KMP algorithm which will reduce the 2 to the m. Okay? KMP is very specific. Don't worry if you don't know KMP. KMP is very specific to not having these don't care symbols. So this turns out to be a more complicated problem. Okay? So the point I'm going to get towards is that I'm going to show you how one can take something which looks like this completely string matching, which has nothing to do with FFTs, and I'm going to use FFT to get a very fast algorithm for this. Okay? Right? Again, illustrating the fancy way algorithms interact with each other. Right? Okay. So let's try to understand this reduction in effect. So why does convolution really help you, right? Let's see what convolution really does for you. Okay? It doesn't seem like it is a very useful operation. So my claim is that it allows you to do something which is a natural operation called shifted products. Okay? So forget about pattern matching. Suppose I give you two arrays A and B. Okay? A is an array of size m and B is an array of size n. Okay? And what I want to compute the following. Okay? I want to compute this array C. What is the array C? I want to compute, think of this, right? Think of B as this, right? Here is B. 0, 0, 1, 1, 1. I'm just using binary alphabet precisely for that, right? So this is B. And A is the other array. So suppose I put A let's call this 0, 1, 1, 0. Okay? So I take B, I put A on top of B at some position, and then I want to compute the product 0 times 0 plus 1 times 1 plus 1 times 1 plus 0 times 1. Okay? So this is the product of A and B at the second position of B. Okay? That is C of, depends on how you index. Let's call it, say this is C of 1, this is C of 0. It depends on how you index it, right? So for every alignment of A on B, I want to compute the product. Okay? Okay? Okay, so what is C for me? So if I align A at this position, what do I get? Okay, so let's do that, right? I always get confused with this. Where is the? Okay. Okay, so what is the definition of? Okay, so first align A at here, right? 0, 1, 1, 0. What is the product? 0 plus 1, 0 plus 1 plus 0. So C is at this position is what? 1, right? Now I want to shift A. Okay? Okay, I have to erase it, right? Okay, so let's keep it, okay, I just shift A here and put it here, right? What is the value then? Okay, 2. And then I want to shift A again. You get the idea, right? Yeah? So I want all those values, not just one of them. I want the full, right? Okay. Normally, if you just do it, you will have to spend how much time? Nm time, right? But I claim that you can do it in n log n time. Why is that? I want to compute C. Okay? What is the connection to polynomial multiplication? Sorry? Sorry, what did I? You treat arrays of coefficients, but you have to do small trick. Yeah, sure, you can add 0, but you actually have to reverse B. This is just an indexing issue. Okay, how can you reduce the multiplication? I will treat B as a polynomial with this as the 0th coefficient and this as the highest coefficient. But A will be this as the 0th coefficient. Why is that? Because if you treat this as coefficients, why will this be the right term in the multiplication? Okay. Okay. So I just want to claim the following, right? to get all these products, I treat B as a polynomial. Okay, what does it mean to treat B as a polynomial, right? To treat the coefficients of the array of B. But I have to treat it as the other way, the reverse of B as the starting point, and A will be the straight way. Why is that? Because when I align these guys, why is it the case that, if you think of this as polynomials, the degree of all these guys should be the same, right? When you think of, okay, let's write this down, right? Okay, so I want to think of this as, okay, what is the size of B, right? 1, 2, 3, 4, 5, 6, 7. So I want to think of this as 0 times x to the 6, 0 times x to the 5, 1 times x to the 4, blah blah, up to 1 times x to the 0. Okay, but I want to treat of A as 0 times x to the 0 plus 1 times x to the 1 plus 1 times x square plus 0 times x cube. Okay, okay. Why is that? Why does that help us? Because then what is the product of this and this? We are multiplying, we are going to get the same degree. This is 0 and this is 6. This is degree 1, degree 5. That's the term we want, right? It's nothing complicated here, okay? All I'm trying to say is that if you want the shifted products, you think of them as alignment, right? If you want all of them, it's the same as taking B, thinking of it as a polynomial going this way, and A as thinking of it as a polynomial going this way. That's when the things will align with the right way, you will get the right answer. It's not complicated, it's just a small trick. Okay? Am I making sense? Okay? You just have to verify that you have to treat B as a polynomial with the 0th coefficient coming from here, and A as a polynomial with 0th coefficient, the coefficient of x to the 0 coming from this way. And then you'll get the right products. Okay? So that is the power of basically FFT. You can do the shifted products in very fast. Okay? Another way of thinking about it is, okay, I can do shifted products now instead of thinking about FFT. Given two arrays, I can do shifted products. Okay, we're slowly, right? Now, as I said, C is the convolutions of vectors A and reverse of B. Okay, that's all. Okay, proof is, you just have to verify that. Okay, now back to pattern matching, right? Now we're going to use pattern, we're going to reduce the pattern matching problem to the shifted product problem. Okay, we know shifted product can be done in n log n time using convolution. So if you can do pattern matching using the shifted products, then we can do in n log n time, right? Okay, so the point is that we'll first stick to 0, 1 alphabet. We're not using A, B, C, Ds, right? Our alphabet is only very small, 0 and 1. Okay? Okay? Is that a simple setting, right? Binary alphabet. Why is that? We'll see why is that. Okay, okay, let's go back to this, right? Suppose this is my pattern and this is my text. How do I find out, where does A match up with B? Right? If you think of that as A as a pattern and B as a text, using shifted products, what can we do? What are we really looking for, right? When does, so to take the same example, so let's take the example of B as, can somebody remember that pattern? A is 0, 1, 1, 0, right? Okay? And B is what? Okay, let's go back. 0, 0, 1, 1, 1, 0, 1. Okay, okay. You guys are better at remembering that? 0, 0, 1, 1, 1, 0, 1, right? Okay, so how do we know how to pattern match, right? Okay, does it match here? No, right? Where does it match, if at all it matches? Maybe it doesn't match anywhere, right? But what do we really want to do, right? To pattern match, we want to take the XOR of these guys and then add them up. Okay? Suppose we could do XOR of those guys and then add them up instead of doing the multiplication and then adding them up. then we'll know, right? Because XOR would mean that we'll get 1 when it is there different. We don't want, right? If you get 0 in that thing, then we know there's a match at that position. Okay? But we don't have XOR plus addition. That's a bit bizarre operation, right? All we know is that, you know, we can multiply term by term and add them up, and that is the position we'll get. Okay? So can we simulate XOR using just this thing? And in the case of binary, you can. And again, you know, it's clever. So it goes back to 1974. Okay? This is Patterson and Fisher. So here is a thing, right? So what we'll do is the following, right? We will say that, you know, if you say put this pattern on this text at some position, we're trying to align it. There's a type 1 mismatch at some place if the pattern has 1, but the, sorry, like I went, oh, sorry, let me go back. Okay. So remember, we have a pattern which is